covered on the web page. Essentially, any of the sections that are listed in the schedule can be, we're going to cover. That's not all the chapters, but just the sections. You can bring a letter-sized sheet of paper with anything written on it. Means you don't have to remember a whole lot of things, and it's actually good to summarize things in a sheet of paper. It's good for learning, and it's... Yeah. It covers up to today, and it also is going to assume you know the content of the assignment. So look at the solutions to the assignments as well. So because some of the things you... the assignments are where you learn everything, okay? They're the things you get to play with something, and then all of a sudden you say, aha, that's what he was talking about. Okay, so the assignments are sort of an important part of this course. Does anyone have any questions about anything? Yes? Yes, you can write on all the sides, all 6 sides, yeah. Any other question? Okay. Sorry? No, there's no Python coding on the midterm. Any other questions? Okay. It's going to be much like the practice. So if you look at the practice, it's going to be like that. They're the sort of things you need to know. Okay. So what we've been doing recently is propositions and inference. And we've got this propositional definite clause language made up of clauses are either facts or rules. We had defined an interpretation as an assignment of a truth value to each atom. A model is an interpretation in which all the knowledge base is true. We have this funny symbol, vertical bar symbol, which means that G is a logical consequence of this knowledge base, or not a logical consequence of this knowledge base, depending whether it's true in every model or there's a model of the knowledge base in which it's false. And we have a bottom-up proof procedure. Effectively did forward chaining on the rules. And we ended up having this minimal model where each element of C is true and all others are false. And that's what we used to show that this was sound and complete. Okay, are there any questions about what we've been doing? Okay. At the end of last time, I tried to talk about false positives and false negatives, and we got all confused, so let's revisit that. So the story is, if you can predict something, if someone tells you have some very bad disease, and you don't have that disease, it's a false positive, right? So on the x-axis, you get to predict. So you either predict it's positive, and prediction is positive, you either predict you have this bad disease, or you don't have this bad disease, and you actually have the bad disease, or you don't have this bad disease. So if you predict you have it and you don't have it, it's a false positive, right? And if you predict you don't have it and you do have it, it's a false negative. So how does that convert to what we did here? Well, predicting is what we're going to do is the proof procedure, right? And the actual positive is what logically follows. So the truth, the real world is this logically follows. This is our meaning, and we have this prediction is our proof. So we could predict positive means this knowledge base logically, this knowledge base does G, or we could have this knowledge base doesn't logically follow. And then we could have the actual positive, or the knowledge base does not. Okay? That's just following those two things. So what does sound mean? Who remembers what sound means? What does sound mean? Come on, someone tell me. If it's proved, you can prove it's true. If the knowledge base, if you can prove it, then it logically follows. So this says if you can prove it, then it must be in this must be in this box. So it means there are no what? Right, it means there are no false positives. So this means this is soundness cuts out this. So there are no false positives. Is that what I said last time? I can't remember what I said last time. I thought you guys would know enough to help me. So, does that make sense? There are no false positives. And what does completeness mean? Someone tell me, what does completeness mean? Yeah. Yeah, if it's a logical consequence, then you can prove it. Right, so if it's a logical consequence, means this is the case, right? We're in this box here. And we can prove it means it must be in here, so it says that what is there no what? Right, so if you're in this column, which is the logically follows column, means you must be here. So what does it mean? So what does it mean there are no? Come on. Right, so no false negatives. So there are none of these. So completeness rules out this. Completeness says there are none of these. Soundness says there are none of these. Completeness says there are none of these. So this says there's no false negatives. It's important you know that people talk about, when they talk about medical things and all sorts of things in the news, they often talk about false positives and false negatives and their problems with tests and things when we talk about whether there are false positives and false negatives. Okay? Any questions about this? Questions? All right. All right, let's do a clicker question. This will test whether you know it. A proof procedure that specifies that nothing can be proved. So for any knowledge base in G, if it's asked whether G follows from the knowledge base, it says no. Right? So nothing logically follows. No, it can't prove anything. Okay? Is it sound and complete? Sound but not complete? Complete but not sound, or neither sound nor complete? So it always says no. For everything it doesn't, you can't prove anything. Does anyone need more time? Okay, let's stop that. Oh, that's exciting. All right. Is it sound? Does everything that can prove true? Well, it can't prove anything, but everything's true, right? So it's sound. So it is sound, but it can't prove everything because it can't prove anything, so it can't prove everything. So it's actually, the answer is actually B. And if you want a sound proof procedure, it's really easy to get a sound proof procedure. You just refuse to prove anything, and you never make a mistake. Okay, if you don't want to ever make a mistake, the best way to not make any mistakes is not to say anything. Okay, that's what this tells you. So if you want to guarantee you don't make mistakes, don't say anything. Because it's a bad policy, you'll fail all your courses and everything, but that's fine. You won't make a mistake. Okay, all right. Any questions about that? Here's the next one. A proof procedure that specifies that everything can be proved. So for any knowledge base and G, if it's asked whether G can be proved, it says, yes, I can prove. It says yes. Is it sound and complete, sound but not complete, complete but not sound, or neither sound nor complete. All right, anyone need more time? Okay, 5, 4, 3, 2, 1. Let's go. It's complete but not sound. Right, if you want to always be able to predict something, you have to be, you've got to be able to say yes to everything. Right, so if you're a magician and you want to be able to say, I can answer every question correctly, what you do is you just have enough pockets you can open and show the right answer in one of your pockets. So you've got to basically predict everything you can predict. So you've got to be able to say yes to everything. Then you'll always get something right. So the magicians who, if you ask them a question, they say, oh, look, it was written in this card in my pocket. But which pocket they pull it out of course, depends on what the question is, because every possible answer is in one of their pockets or somewhere that they can marvelously say, here is the solution. So if you want to answer everything, be complete, then it's easy to be complete as well. You just got to say yes to everything. So being sound and complete is what's difficult. Any questions about that? Okay. So here is the question from last time, the same one as last time. Foo if bar and sad, bar if grew. Whoops, I should start it. Grew, sad if bleen, and then which of the following is a fixed point, which is the consequence set C when the Foo's procedure holds. Remember that? The fixed point was the consequence set when the bottom-up procedure holds. Is it all of them? Is it none of them? Is it just grew? Is it foo, bar, and grew, or is it bar and grew? Okay, I'm going to need more time. No. Yeah, the answer is E. Some people said C. Right, C is not the answer, because although you can prove G, once you've been able to prove G, you can also prove bar. Remember the procedure said if I have a rule, first of all, I can immediately prove G, grew, so at least everyone knows that one. But the other one says if I can prove grew, then I can infer bar. So we're going to add bar to it. But then there's nothing else we can do. We can't add foo because we don't have sad in there, and we can't add sad because we don't have bleen, and we can't add bleen because there's no rules for bleen. Okay? Any questions about that? So the answer is E. And let's do one more. So consider this knowledge base, and before we used this as an example of the one that had meaning to us, but now it's just symbols we're going to play with. So the computer's just thinking these as just symbols. So lit L1 if live, so lit L8 if live. Oh, you can read that. And in the bottom-up proof procedure, we currently have this consequence set, and I want to know which we could add in the very next step, which we're allowed to add. How are we going? Do you need more time? Anyone still need more time? Okay, let's stop. Yes. Yep, the answer's B. Okay, if you go through it, good. Any questions about that? We can add, so the answer is A because we can add live W1 because we have live W3 and up S1 in there. We can't add live W0 because we don't yet have live W1 in there. So it was always about the next one. Any questions about that? Okay. All right. So what we're going to do is we're going to do a top-down proof procedure, a different sort of proof procedure that we did before. It's called SLD resolution. We're going to be able to trace this top-down proof for definite clauses. And so when we did it before, we essentially derived everything that could possibly be true from this knowledge. So in the bottom-up proof procedure, we derived everything, right, that could possibly be true. And as you can imagine, for big domains or systems, deriving everything that's possibly true is a bit much. What we'd like to instead do is to have a knowledge base and a query, and determine whether this query follows from this knowledge base. So we're going to start from the query, and we're going to say, can we prove it? And we're going to do a search backwards from the query to determine if something's a logical consequence. We're going to start from some query, and you say, how can we actually start off proving this? Okay, so that's what we're going to do. So we're going to start off with this funny thing called an answer clause. An answer clause says yes, and yes intuitively means we've answered the question. If we can have yes, then we've answered the question. We have yes if we have this body. So it's just a clause that we've seen before, except it has this funny head called yes. And then we're going to be able to do what's called a resolution of this with some other clause. A is true if with some other element of the body, and we're just going to replace the element of the body. We're just going to replace AI in the body with B1 to BP. So if we have yes if A and B and C, and we're going to do the SLD resolution of this on, and we also have B is true if E and F. Then together of these, so we've got to have this answer clause. We're going to do the resolution on B. The resolution, the SLD resolution on B. All we're going to do is replace B here with E and F. So we get yes if A and E and F and C. Does that make sense? All we're doing is just replacing this element with the body. And often we're going to just to show what we're doing here is we're sort of going to underline the one we've selected here. And then if we had the rule that said E, if we had the rule that said A if, I don't know what that is. Okay. If we just had A by itself, we can resolve this against A and just get yes if E and F and C. Okay, so this is just a special case when M is 0. So this is the SLD resolution of these two. So this one here is the SLD resolution of these two, the SLD resolution of these two. Whoops. The SLD resolution on A replaces A in here with the body, so it gets rid of it. Oh, you guys probably can't see. Hang on, I'll like this. So make sense of what's happening. All we're doing is replacing this body. We'll get used to it. We'll see lots of examples in a minute. All right. So then what we're going to do is we're going to try and do this until we get to the case of where we have an answer clause with m is 0. So we're just going to keep doing this until we get rid of every body. So we've proved every element of this body. So we end up with an answer clause that, this is just called an answer. It's just yes by itself. And then we're going to have a derivation from some query from a knowledge base as a sequence of answer clauses such that we're going to start with the answer. We're going to start with yes if the query is true. Okay. And then we're going to resolve the previous answer clause with a clause in this knowledge base. And we're going to finally end up with an answer. Okay, let's have an example here. Hang on, I think I can show both at the same time. So we'd like to, so here's a sort of a silly clauses. So let's try and build a derivation from this. So the query is clap. So what is the rule? What's the first thing got to be? So then we're going to do a derivation. Derivation of clap. So what's the first thing we do? We just follow the rules. What does it say? It should be yes if clap, right? Yes if we clap. And now we're going to get this, select something here, the clap. I'm going to replace it by the body. So we're going to say yes if we're happy and we know it. So right, and then we're going to select one of these, and I'll underline it. And we're going to say we're happy if we're healthy. So we're going to say yes if healthy, and we know it. By the way, according to the system, these have just funny symbols that don't have any meaning to it. So, okay, and we're going to select one of these. So we're going to collect healthy. We're going to replace it by the body. So we're going to have yes if we know it. Whoops. Know it. And we're going to select this one. And it's going to be, we're going to replace it with its body, so we're going to have yes. Okay, that makes sense? All we're doing is this very simple thing. We're just replacing this with the body. So this is a rule, right? And this is a rule. And this is the rule that says it's healthy if nothing, and know it if nothing. Okay, any questions about that? What? Yeah, I don't know. Okay, any other? So now what we're going to do, so now we're going to solve this query. We're going to have this, so now we're going to have this funny, so here's my top-down interpreter. So I'm going to solve this query, Q if Q1 up to QK. I'm going to have this answer clause that's going to start off with yes if I query it. Then we're going to select an atom from the body of this answer clause. We're going to choose a clause from the knowledge base with head as the body. And then we're going to replace AI in the body of the answer clause by the body of this clause until we have an answer clause. Okay, so this is, so according to, so if you look at this, there's two different words in here that we sort of have a different funny meaning of. One is select and one is choose. So these are actually different in the sense that one is so-called don't care non-determinism. If one selection doesn't lead to a solution, there's no point in trying other alternatives, and that's this select. And if we can have don't know non-determinism, says if one of the choices doesn't lead to a solution, other choices may. And these, if you go to an operating systems class, they talk about non-determinism. They almost invariably mean don't care non-determinism. You have to non-deterministically select the next process to run. And as far as, well, you just basically select one. If you selected the wrong one, you throw it away and you just go to the next one. Whereas if you talk about NP-hard problems, then it's almost invariably don't know non-determinism. You've got to select the correct one if there's an oracle that has to select it for you. Okay, so that's the two things. Different courses, different words, non-determinism in different ways. Here we have to tell it to you because we're using the same, two different sorts of non-determinism in the same algorithm here. One is a select. We don't have to backtrack on it. And the other is a choose. We might have to select from it. Okay. So let's give an example of a derivation here. And you have to help me because I can't see it. My neck doesn't go that way. So I'm going to say yes if A. And I have to choose one of the clauses. I have to choose one of the clauses. Two clauses for A. I get to choose one of them, right? It says I should choose one of them. And because we have an oracle, I'm just going to choose one of them. I'm going to choose the second one. So I'm going to say yes is true if E and F. This is my choice. I get to choose this one. So I get to choose this clause. And now I get to select an atom. Which one should I select? Well, it turns out it doesn't actually matter. This choice matters for whether I'm going to prove it or not, but the selection here doesn't matter. I can select whichever one I want. So I'm going to select one of them. I'm going to select one just arbitrarily, E. And now I'm going to choose a clause. Which one should I choose? I can't see. My neck doesn't work. Which one? Just E by itself, right? Okay, so what do I end up with here? Yes? Oh, I can't see. It doesn't work. Yep. Yes if F, right? So now I'm going to select one. There's only one to select. There's two? All right, good. Which one should I select? No, there's only one F to select. There's two to choose between. There. E and F. A is true if E and F. I got rid of E. F if C, is that right? Yeah. Oh, sorry. I actually should write down here. Hang on. Let's write this. So here I'm going to choose A is true if E and F. Here I choose just E. Here I'm going to choose what? F if C. And I'm going to end up with yes if C. Then what am I going to do? I'm going to choose C if E. C if E. They're going to end up with just yes if E. Then I'm going to choose what? What is dance? I'd choose D here. I'm going to choose it again. No, I'm going to choose just E, and then I'm at yes, and I'm done. Does that make sense? What if I'd chosen, I chose A if B and C. Oh. So what happens if I chose the other one? Well, what would I end up with? I'd end up with, so I end up with yes if A. So I'm going to start off with yes if A. Then I'm going to go to yes if B and C. Okay, so I'm going to choose A if B and C. Now what happens here? I'm going to select let's select this one. What? Choose B if F and K. Choose B if F and K. So then what do I end up with? F and K and C, I heard someone say. Then I'm going to choose one of them. Which one should I choose? Which one? So I should select K. Someone suggested I should select K. What should I choose then? There aren't any rules for K, are there? Right, so there are no choices. So in fact, this fails. This is the failing derivative. This is said to fail. Does it make sense to research now? Look, I selected K here because someone told me to. It would have made a difference if I'd selected F. Yes, it didn't matter. So when I selected this one, I actually sort of wanted to select the one that's going to fail earliest. So I wanted to be a troublemaker and say, let's try and fail as early as I can. Okay, so here I selected K because it failed quickly. But I had to sort of choose the correct one. Okay, so this is what we're going to mean by this sort of select and choose. So I get to select one here. I'm sort of going to select things that I want to. I'm going to select things as a troublemaker. I'm going to select K. But now I'm going to choose. But I have to choose, I have to do this oracle thing. How am I choosing it? How do I implement oracles? How do I implement oracles? We did this before. So an NP-hard problem, we have to choose. How do you get oracle? How do we implement an oracle? How do you implement oracles? Yeah, but we know that doesn't exist. We know we can't implement that, so how do we implement it? How do we implement NP? How do we solve NP-hard problems? We've been spending most of the course on how solving NP-hard problems. You can solve it by brute force. Or you can search. You can search. We looked at searching. Yeah. Yes? And then how do you get F in the next one? When we choose E, we replace D with the body, and there's an empty body, so we're going to just get rid of it. But actually, are you like selecting it, or are you choosing? I selected E. I select an element of the conjunction. I select one of these, but then I chose a clause. This is a clause. I choose the clause E. That's important. I choose the clause E-U-S, the clause E. So choose the clause. I choose clauses. Right? If you look at the thing, I say choose clauses. So this is the clause by itself, E. It's just a fact. And I replace E by the body. It has an empty body. So I'm going to get rid of it. I'm just going to put F there. Right? But I select, when I selected things, I selected an atom in the body. So I select an atom from the body, and I choose a clause. Okay, any questions about that so far? So here's a different example. And so now what we're going to do is we're going to look at how to implement It's now going to work out how to implement the searching. So what we're going to do is we're going to start off with this query as A and D. The query is A and D. So I'm going to, that's my query, A and D. We're going to replace that with yes if A and D. And now there are three possible choices we could do. So we're going to select one. We can select an arbitrary one. We can select A. We can choose one of the three clauses. What are they? A if B and C. We could choose A if G. Or we could choose A if H. Right, now we have A, F, B, and C. What do we get in here? We have a choice of these three. We don't know which one we're going to do. If we don't know which one we're going to do, we're going to search over them, right? So if A, F, B, and C, what's the rule for I had this, I selected A, I chose this. What do I end up with? Yes, if B and C and D. Okay, so now I'm going to select one of them. Which one should I select? Pick one. I don't care. B. And now I have a choice. What are the two rules I could choose from? Sorry, I can't hear you. What? B if J and B if K. Okay, now I'm going to go here. And what do we end up with here? Yes, if J and C and D. And what should I select? C, someone said? Someone said J. Let's do J then. The loudest person said J. We'll do it by loudness. Okay, we're going to select this. There are no clauses. Right, so in fact this one here, it fails. Because we're searching, we know how to search. We're going to go back here and we're going to backtrack to this one. Right, we're now going to backtrack to this one and we're going to get yes, if, what is it? Now what can I select? So well, it's two things, right? There's only one KFM. Right, KFM, then we're going to have, what is it? Yes, if M, oh, that's awful writing, sorry. Yes, if M and C and D. And what are we going to select? M. And what do we choose? Are there any rules for M? There's nothing to choose. Right? There's no choice available. I have to choose something, so I can't choose this. So what do I do now? I've gone down here, I've backtracked up here, I've tried this. I know this one doesn't solve anything. I know this one here doesn't do it, so I'm going to backtrack to here, and I'm going to go to here. This is just depth first search, right? We've done this. Let's keep going. So AFG, what do we get? Oh, we get yes if G and D. Oh, I changed color. Oh, well. Now I'm going to select one. Which one should I select? D? D, okay. I don't mind. Why do you get to choose one of these two? What are you talking about? I'll choose this one. I don't care which one it is. D if M. D if... There's two rules. There's two rules. D if M. Whoops. There's D if M. And there's D if P. And D if M gives me yes if G and M. And then are there any rules for M? Do I get to choose something? What can I choose? I don't think there's any choices, is there? Now I'm going to choose, oh, I've got time. Does that make sense? Any questions about that? I'm going to choose this one. What do you get? You get D if, you get, what do we get? Yes if G and, yes if G and P. So what should I select? What do you suggest I select? G. And what do I end up with? Oh, no, I end up with two things here. I end up with, I can choose, what are the two rules for G? G if M and G if F. And what happens if I choose this? So I end up with yes. I'm searching. I'm not an oracle. I don't know how to be an oracle. I'm just a dumb computer. Well, I was an oracle a minute ago, but not now. Now I'm just a dumb computer. I search. That's how I do it. I just blindly search, right? Yes if M and P. Right, now I'm going to select something. What else did I select? Select M. And what do I get? What are my things? X. Oh, I'm running out of space. So I go here. What do I end up with here? Yes if F and P. Choose P. What should I choose? I don't care. P. I'll choose F then. I don't care. What am I going to do? What am I know, children? No, I'm going to boom. I'm being FFM. I'm doing both. I'm searching. I'm searching. I don't know how to implement an oracle. I'm searching, right? Yes, if M and P. Which one am I going to select? Is there a rule for M? No. So then I'm going to end up with here with yes, if P and P. I'm going to choose one of them, select one of them. Which rule am I going to use? Use P, right? So I'm going to use P, which is by itself. So I'm going to get yes if P. And then I'm going to end up here, I'm just going to do with just yes if, right? And I've succeeded. So my computer can implement an oracle by search. So if you want to know how to solve NP-hard problems, you search. Right, we end up with this, have to search through this. And if people who've done 322 in the prologue will know this is exactly how prologue works. 312. Oh, they're all funny numbers to me. It's okay. So if you go through 312, the logic program, this is how prologue works. It's just a slightly richer language than we've done there, not very much richer. Okay, we end up with a solve in here. So the nodes who answer, so in here, so we've got a search space. So in the search, remember a search? So what's a node correspond to? Remember the search is defined in terms of the nodes, the neighbors, the goal, and the start, right? So what's a node correspond to in our language you've seen so far? Right, it's an answer clause. A node is just an answer clause. Right? The neighbors are obtained by selecting an atom, and then the neighbors correspond to all the rules for that atom. So you select an atom, and there is a neighbor for every rule. For every rule, for every clause, a clause with the atom at the head. And the goal is just this yes if, and the start is just a yes if my query. Okay, so this is how we're going to abstract in a search. So now we know how to solve these things. It's just search, right? You know how to implement it because you learned how to implement search. Okay, any questions? So the midterm exam's up to the end of today. Okay, let's stop there. Thank you.